Welcome back to Chapter 25. In this video, we'll be discussing the binomial distribution, the first of two probability distributions having to do with discrete random variables. Please have a calculator handy, as I'll be referring to it quite a bit in the following. So what is the binomial distribution? It's just the probability distribution when we are sampling with replacement and a few other criteria are met. Those criteria are when we perform our experiment, when we're sampling, either one of two outcomes must occur. So we usually call them success or failure. As there are two outcomes, that's kind of where the name binomial comes from. So my first criteria is that there must be binary outcomes. Second criterion, the trials must be independent. The third criterion, we must decide in advance what the number of trials of our experiment will be. And the fourth criterion is that the probability of success remains the same in all of those trials. And just to briefly mention, if we were to sample without replacement, we'd actually be using a different probability distribution, which is not part of this course. It's not part of the stats option. It's not part of AP stats. But if you study statistics in university, you might run into it. First, I want to look at a interesting connection back to the binomial expansion. And we'll see how that relates to probability in this particular example. So part A, expand 9 over 10 plus 1 over 10 to the power of 5. Now, don't be clever and tell me the answer is 1. We want to actually expand that binomial. So we use binomial expansion, and we get this lovely thing. And what does that have to do with this probability down below? Well, I notice that we've got 90% chance of hitting a target, so 90% success, which means there's going to be 10% failure. And of course, our success for our probability for success and our probability for failure have to add up to get us 1. 9/10 plus 1/10 is 1. That's great. And we are going to fire 5 arrows, and that connects to that exponent right there. So looking at our expansion, the probability of hitting the target twice only. That means we're going to have 2 successes but 3 failures. I'm looking right here. So we're just grabbing our calculator and multiplying that out. 10 times 9/10 squared times 1/10 cubed. And we got our decimal right there. And then the second was hitting at most 3 times. So that means we could be hitting 3 times, but it could also be less than that. So we're going to add up those 4. Again, grabbing a calculator to 3 significant figures, that's our answer. I guess technically you could also draw a massive tree diagram, which I am not going to draw the entire thing for here, and then just find all of the roots through it that have exactly 2 successes, or whatever it is that you're looking for. But I really don't recommend that. For binomial probability problems, we're going to have generally a large number of trials, so tree diagrams are going to become unwieldy very quickly. Just another minute about non-calculator techniques, just in case, and also what work you'd be writing down. So if we have a situation where a binomial distribution is going to show up, let me just state this right here. This should appear on our work. We're saying here that our random variable x is distributed as a binomial distribution with n trials and a probability p of success. This information is literally all that you need to know about a binomial distribution to figure out what any probability is. You need to know how many trials there are, and you need to know what the probability of success is. Think back to the last problem. That's all that was important there, right? So that's, if you write that down as your work, the next line can be your answer, assuming this is paper 2 and you've gotten your answer from a calculator. So that's super important. Next, also flipping through this blue box, we see, and this was used in the previous example, that if we have a binomial distribution, that the probability that our random variable x takes on a specific value r, that will be equal to our binomial expansion n choose r times the probability of success to the power of r times the probability of failure to the power of n minus r. This is in your formula book, so you don't need to memorize it. Also in your formula book is the fact that the mean, or the expected value of a binomial distribution, is always equal to the number of trials multiplied by the probability of success. Okay, but since like the vast majority of problems for this topic are going to be with a calculator, let's get down to business and see how we would do that here. So I'm going menu, I'm going statistics. This is a statistics problem, right? I'm talking about a binomial distribution. So I'm going here, and then I just got to look through this list. Now there's two things that say binomial. There's PDF and there's CDF. For our first problem, when it's the probability of finding a specific number of successes, we're using PDF. I like to pretend that the P stands for particular. Choosing that, in the previous problem we were told there were 5 trials. The probability of success was 90%. Like I said, that's all the information that you needed to know. Now if I just type this in, I get a list of numbers. And what that list of numbers is telling me is, in order, the probability of getting 0 successes, 1 success, 2 successes, that number should look familiar, 3, 4, and finally 5 successes. So it'll just output a list of the probability of any number of successes you could possibly have wanted. If I went back and I put in a specific value, then it'll only give me the probability of that number of successes. So what about the second problem, where we had at most 3 successes? Well, this is going to be the CDF. I like to pretend that the C stands for cumulative. So in this case, again, there were 5 trials. Probability of success was 0.9. My lower bound of successes for this problem was 0, and my upper bound was 3. So that right there, that is the major takeaway from this video, is just knowing how to use the calculator. Because again, most questions for statistics are going to be calculator based. That being said, let's look at some problems together. This first one I'm not going to elaborate on, just checking to see whether the binomial distribution actually applies to these various scenarios. So read it through, make sure they make sense. The last one might be a little bit tricky, but I assure you those answers are correct. So now let's do a problem. So I've got apples in a crate. 5% chance that one of them has a blemish. We're taking a random sample of 25 apples with replacement. So we are taking one apple out, checking to see if it has a blemish, replacing it in the bin, and then we're taking another apple out. We're going to use 25 times. There's a chance that we will choose the exact same apple 25 times. That's fine, because if we take a sample of 25 apples all at once, it's not going to be binomial, so then we're going to have to use the hypergeometric distribution, and we don't know how to do that. So anyway, we're going to go to our calculator, because this problem, this random variable x, is binomially distributed with a sample size of 25, because we're sampling 25 apples, and a probability of success of 0.05. So we're going to grab our calculator. For letter A, we're going to use binomial PDF. We're going to get 2.231. For letter B, we're going to use binom CDF. Now we want at least 1 to have a blemish, so our lower bound is going to be 1, and our upper bound is going to be 25. We find a probability of 0.723. That kind of makes sense. Like, we would expect at least 1 to have a blemish, even though there's only a 5% chance that any particular apple has a blemish. Since we're choosing so many apples, we expect there to be at least 1 in the group that does. And then for letter C, the expected number of apples that will have a blemish. So if we were to do this sampling of 25 a whole bunch of times, what would be the average number of apples that have a blemish? And I'm getting 1.25 because we're taking the number of trials, n, and we're multiplying it by the probability of success, if you want to call finding a blemish a success, and you'll get 1.25. Okay, next up, we've got, I'm seeing a percentage. That's going to be my probability of success. I'm seeing a number of patients being treated with a drug. That's going to be my n. So that's my work that I'm going to put down. And we want to know the probability that between 24 and 31 patients, inclusive, will be cured. So that means we're going to do CDF, and our lower bound is going to be 24, and our upper bound is going to be 31. And then you get your answer. As you can see, this is very easy once you know what you're doing with your technology. All right, next up. I don't know why the book included this first bullet point earlier about what the mean of the binomial distribution is, but it didn't mention the standard deviation, as I'm sure you were wondering. So here it is. Standard deviation is square root of NP times 1 minus P. That is not in the formula book, but the variance is in the formula book. So obviously just take the square root to get the standard deviation, which is more often than not what we're actually interested in. And all this stuff is hanging out down here in section 5.6. We've got the rule right here, and we've got the binomial expansion showing up again here, and your mean and variance. So given that, let's perform some quick calculations here. We've got a sample size of 30. We've got a probability of being defective, we'll call that success, as 0.04. So knowing that, the mean and the standard deviation of this distribution, the mean is then just going to be 30 times 0.04, and then the standard deviation will be our square root of 30 times 0.04 times the probability of failure, which is 0.96. Letter B, we're talking about a different distribution. This is y, which is binomially distributed. Y is the number of non-defective